Hello everyone, welcome back. Today we are going to discuss a recent paper called W2V-BERT, combining contrastive learning and masked language modeling for self-supervised speech retraining. This paper is a collaboration between MIT Seaside Lab and Google. And the overview is as follows. First we'll see the introduction of the paper, then we'll see the methodology of the proposed approach, then we'll see the experiments, and finally we'll see some results. So the idea is very simple. The paper talks about combining masked language modeling trick, which is used to pre-train BERT and other models, and contrastive learning. And as you know, W2V 2.0 model uses contrastive loss along with the diversity loss, of course, for training the model. And this paper proposes to use masked language modeling loss in addition to the contrastive loss. We'll understand what is masked language modeling loss in the coming slide in detail, and also we'll understand what is this contrastive loss, which many people will also maybe already knowing, because if you know about the W2V paper or any other contrastive losses uh, proposed in previous approaches, previous papers, you will know about contrastive loss. But we will explain in detail how this paper uses contrastive loss and masked language modeling to train or pre-train pre-train acoustic model so that it can be fine-tuned for downstream tasks such as speech recognition tasks. And this paper shows that this W2V-BERT, the proposed approach, obtains state-of-the-art performance for LibriSpeech as well as their in-house Google voice search dataset. And we'll see the numbers and so on, and also it outperforms the Hubert paper, the model. So Hubert model is a hidden in its BERT model. So that paper, that approach also uses something similar to this idea, but not exactly masked language modeling, but it uses clustering and clustering approach of clustering of the contextual representation, and uses those clustering IDs and forces the model to predict those clustering IDs in order to learn better representations of the acoustic data. So we'll do the comparison and so on in the coming slide. And the methodology is as follows. First we'll look at the model architecture, and then we will see the contrastive loss. Not exactly contrastive loss, we are going to look at the W2V loss, because the paper refers to this W2V 2.0 loss, or W2V 2.0 models loss as the contrastive loss here. And in addition to that, they are using this masked language modeling loss. We will see that, and at the end we'll understand the fine-tuning procedure, which is kind of similar to the W2V approach, but it's not completely similar. There is some changes, so we will look at that. This is the model architecture. As you can see, the model takes input features. Unlike in W2V, it takes the raw audio as input. In this case, they take a sequence of feature vectors, and they are log spectrum, mil spectrograms, and those features are some dimension, let's say f, and they will have, let's say, the number of frames are t, and this is the matrix f cross t, and this is going to be the input to the feature encoder. So this is the feature encoder. Unlike W2V, these guys use 2D feature 2D convolution layers to process the input features, whereas in case of W2V, they use 1D convolution layers, because the input signal is one dimension, right? And after the convolution layer or the feature encoder, you will get the encoded features as output. This is similar to this. This encoded features is basically again a sequence of vectors, and each will be of some dimension. For example, consider as 512, and the number of frames will be depending on the downsampling you are doing on the time axis. Basically, if you using the convolution layer, and yeah, I mean, if you depending on how you choose the convolution layers parameters, for example, the window size and the strides and so on, this number of frames will be depending on that. So assume you are doing downsampling by 4, so that you have chosen the convolution layers parameters such a way that your final number of frames will be 4 times less than the original input dimension, and number of feature vectors, I mean the dimension of the feature vector always obviously changes from f to something else depending on the number of filters and so on. And using this we are going to apply a masking to this feature encoded feature, or sometimes also known as Z or latent representation. So this Z will be masked using masking technique as similar to wave-to-wake. In case of wave-to-wake, we choose a particular index based on some probability, or a particular frame based on some probability, and we decide whether we want to mask out the next L frames. If L is 10, we are going to say, okay, if I choose this frame, I'm going to mask the next 10 frames. Masking in the sense you can simply make them as zeros, but they don't make it as zeros. They actually replace it with some vector. In this case, they are replacing with some random vector, whereas in case of wave-to-wake, they used a particular vector, and they replace the masked vector by that particular vector. In this case, they are simply replacing the masked vectors by a random generated vector, right? And after that, they apply a linear layer, and then the output of linear layer goes to the context network. In this case, the context network are divided into two parts. One is having n layers, and another is having m layers, right? And as you can see, this conformer block is called or the conformer block which has the n conformer layers is called contrastive stack, and the other stack is called MLM stack. So basically, the output from linear layer goes into the contrastive stack, which consists of n conformer blocks, and the output of that is going to go into the contrastive loss, and also it is going to go into the MLM stack, right? And the output of MLM stack is going to go into the MLM loss. We will see what MLM loss is, what contrastive loss is, and so on. And that is the first part. Then once this is done, we are also going to take the extracted features from the feature encoder and feed it to the quantizer. So the quantizer is going to use product quantization technique in order to quantize the encoded feature vectors into target vectors Q, which can be used to run the contrastive loss or compute the contrastive loss, right? And also we are going to use those quantized vectors and create discretized IDs, which are basically sequence of numbers. And let's say if the numbers are in between 0 to 100, you will get like 10, 5, 6, and so on, these kind of numbers. And then you can use the output of the MLM stack and the discretized IDs to compute the MLM loss. So the MLM loss basically here is contrast the contrast CE loss, cross entropy loss. So basically the MLM output will be probability values, and the discretized IDs are the targets. You can simply compute cross entropy loss, which is the MLM loss in this case. And that is done only for masked output, not for masked inputs, not for all the inputs. So we will see that in detail. Hope you guys understood the architecture. It's very simple. You have feature encoder, and then you have two stacks. One stack is called contrastive stacks, which is the output of which is used to compute the contrastive loss, and you have another stack called MLM stack, which the output of which is used to compute the MLM loss, right? And you combine both the losses, like by adding them together, and you train the model end to end, right? As simple as that. Now let's understand how contrastive loss is used in this case. As I mentioned, contrastive loss equation is this, right? And as you know, contrastive loss is a similarity to find out the similarity between CT and QT. QT here is the quantized version of quantized output, and the job of this contrastive loss is to predict or identify the true quantized output or true quantized vector qt for ct or the time step t, and identify them uh, in the presence of distractors. So basically the model has to identify, okay, given set of distractors, let's say k distractors, which are denoted as qt here. It's a pool of distractors which are selected from different mass time steps, and the job of this model is to predict the correct one out of this um, k number of distractors, and one of them is the true quantized representation qt, so that will have higher value and these should have lower values, right? And you normalize it by log, and that is your contrastive loss, right? And then the paper also uses something called diversity loss in order to efficiently use all the code vectors from all the code books, and that is denoted here or shown here, which is basically average entropy of the of p's. So p's are basically, so p is pg is basically sorry, h is nothing but the entropy equation, as you guys know, p log 1 over p, and if you take p up, so you will get minus p log p, and this minus gets cancelled, now you will get this equation. And here g is the number of groups, and v here is the number of code vectors within each group. So the reason why they do this is you have this long sequence, long vectors, right? So you have encoded from feature encoder you get sequence of vectors, and these feature vectors are like very high dimension. Sometimes it is 1024, sometimes it is 512, right? So what you do is, instead of quantizing this entire vector, so you can simply split this vector into sequence of split this long vector into pieces. Let's say you based on number of groups, if you say now I want g to be 4, you can say you can tell the model, okay, split this into 4 parts and then quantize each of them separately, right? And after quantizing, you can just combine all the quantized vectors into a single vector, right? So that is the idea here. So that's why they use the product quantization approach instead of directly going with the normal quantization. And in order to train the model, so again here the p here is just a probability of selecting a particular group and a particular code vector, which is nothing but this equation here. And in this equation you have this variable nv, which is basically the something, it's called Gumbel noise. And why it's called Gumbel noise is because the equation is like this: minus log of u. U here is basically chosen from a uniform distribution 0,1. So it's a random variable, and it's a uniform random variable between 0 and 1, and that's why it's called Gumbel noise, and it's developed by Gumbel. So it's a Gumbel trick to train the wave-to-wave model. This is like a continuous version of argmax, right? And L is basically is what is a predictor from the model, and so the model actually predicts a matrix of I think G cross V, and L is one entry of that particular matrix, and then you plug it in here, and then you can compute this PG and compute the diversity loss. During backpropagation, they use the straight-through estimator in order to compute the backpropagation, and this is how contrastive loss works. I mean, it's quite heavy in detail, but if you understand wave-to-wave paper, it's obvious. So I mean, if you want to understand wave-to-wave paper in detail, I have a tutorial for that as well, so you can check it out. But this is how the contrastive loss is designed, right? That is one loss, which is what is used in case of in the case of wave-to-wave training or wave-to-wave 2.0 model training. Now this paper shows, or this paper proposes to use another loss called masked language modeling masked language modeling loss. So the idea is very simple. So you take the output from the MLM stack, which is the last layer's output, and then you just pass it through softmax layer in order to predict probability of that particular probability at time. Let's say you choose time time steps t, and you have ct, you feed it to a softmax classifier and predict the target probability distribution, right? This is the probability distribution. And so given that, you can simply compute your you simply use a cross entropy loss in order to compute cross entropy loss is very simple, right? You have the probability distribution and you have the ground truth token. You can simply get the loss, right? So that loss is called LC here, sorry, LM here, and LC is the contrastive loss, which I showed you in the previous slide, which is a sum of contrastive loss plus diversity loss. And these two losses, you can add them with some scaling, beta and gamma, and then you get the final loss, which is what is used to train this whole model, right? That is the pre-training loss. And coming to the fine tuning, in case of wave to wake, the way they did the fine tuning was just by adding a CTC layer on top of the contrastive top of the context network, right? So let's say, for example, if this is your wave to wake model, you have input and you are divided into feature encoder and context network, and for the output you just add a linear layer or a projection layer, which is going to predict the probability distribution of the grapheme sequence of that particular language, right? And so you just takes the output, and this is a CTC layer. So CTC layer, and you use a CTC loss in order to train this model, in order to train the speech recognition model, just like deep speech. There you have your speech recognition model, right? But in this case, they are doing it in a different way. What they do is they take this pre-trained model, right, and they consider this as an encoder, right, and they attach a decoder, which is an LSTM decoder, and they connect these two, and they look at this as a sequence to sequence model, right? And it takes the input, and you can predict the output in a sequence to sequence fashion, as simple as that, right? So this is how the fine tuning is done in this case. And as a matter of fact, recently one of my paper got accepted into interspeech. In that paper, I show that using this kind of approach, using this kind of sequence to sequence approach, kind of gives you lower accuracy compared to using CTC layer, right? In this case, they don't have any comparison between CTC approach and the sequence to sequence approach, but in my paper I show that obviously it was done for low resource data. I mean, the fine tuning data was like quite small, like 40 hours of data, and the model was not so accurate, or model was not so good when we had fine tuning in the sequence to sequence fashion. Whereas the CTC layer approach was working quite better than, or much better than the sequence to sequence kind of setting. But in this paper they show, I mean, they don't have any comparison obviously, but I believe they get better accuracy this way, or better performance this way compared to CTC layer. I think it's because of the data. I think it depends on the data also. So that is the fine tuning approach. So now coming to the experiments, they use in-house data as well as some open source data sets like LibreSpeech, and for the inputs they use 8 dimension log-mill filter bank energy coefficients for the energy coefficients as an input, and then the output, the transcript, the output usually in the case of, or in the previous settings, where in the previous settings, in the sense in the previous papers like wave to wake, they used to use graphemes as the output, like the sequence of grapheme units of that language, like in case of English 26 characters. But in this case they are using word-based model, and maybe that is the reason why the model works better in the sequence setting, right? And looking at the architecture, they have two models. One is called W2V-BERT XL and XXL. And in case of XL, they have 12 contrastive layer and 12 masked layers, which is 24 layers of transformer, which is similar to W2V large, right? W2V 2.0 large model in the previous paper. And in case of XL, they have contrastive layer 12, but huge number of masked layers, which is like 30, and the number of parameters is also like crazily high, like 1 billion parameters. And these two are the models. And this is the result section where they have made comparison between different models, and previous approaches and so on. So as you can see here, if you train a conformer model from scratch, you will get decent or okayish results, and obviously you don't have any unlabeled data. You are using supervised approach here. And in case of self-supervised, if you use conformer with NST, which is noisy student training approach, which is again proposed by Google, the same authors I believe, and you will get good results, and the paper has shown that already. If you do only pre-training, I mean, if you don't do self-training, obviously, if you only do pre-training, there is Wave2Vec 2.0 model, so which was published last year. Then there is U-BERT large, which is again a recent paper from I think it's a collaboration between Tesla, CMU, and Facebook. And you have U-BERT large from the same paper. Conformer Excel Wave2Vec is a Google paper. I think some of the authors in this paper are also there in that paper. And this paper's approach, right? And as you can see, most of the time this paper, the proposed approach works better, as you can see here. And if you do pre-training plus self-training or noisy student training is what they call, you can get sometimes this proposed approach works better, and sometimes other approaches like the Wave2Vec conformer works better, as you can see here, right? And this is the results for 100 hours of subset 100 hours of LibreSpeech supervised data, and the baseline models are Wave2Vec and Wave2Vec conformer and BERT Excel, which is this proposed approach. As you can see, the proposed approach in this paper works almost all the time, works better than outperforms the previous two approaches. And they have also done some ablation study on which layers of the transformer layer you should choose in order to get better performance and so on. And finally, they report results on their in-house Google voice search dataset. And as you can see here, this is quite surprising. As you can see here, the proposed approach in this paper works. I mean, gives you a really good really good improvement compared to the previous approach, which is the Wave2Vec conformer, which does not use MLM loss but uses contrastive loss. But the only difference between the Wave2Vec 2.0 original paper and this paper is that they use the conformer blocks instead of transformer blocks, and they also have noisy student training on that. But in this, as you can see clearly, the adding this masked language modeling loss on top of the contrastive loss kind of gives you a really good performance improvement, both for LibreSpeech as well as the in-house data sets from Google, like the Google voice search data and so on. So this is the very nice studies, and this is the very nice approach also. I think the idea is really good. I recommend all of you to read this paper if you are interested, like if you want to gain more understanding or more insights into what's happening, and if you want to see some more tables of or some more results and so on. And yeah, that's all for this tutorial. Thank you so much for watching. If you like this video, please give a thumbs up, and if you want to see more of these kind of tutorials, please subscribe to my channel. Thank you.